Electronegativity is a measure of an atom's strength of attraction for electrons. When two atoms bond, we consider the difference in their electronegativity in order to predict the type of bond that will form. If there is little or no difference, then it will be a nonpolar covalent bond. If there is a noticeable difference, greater than 0.4, then it will be a polar bond. We illustrate the bond polarity as follows. Let's consider HBr, which was example B from the Molecular Shape Lab. Since bromine is more electronegative, it will pull the shared or bonded electrons closer. Since the electrons have a negative charge, then the more electronegative atom gains a partial charge. We write the small delta symbol to indicate the partial charges on the bonding atoms. It is not a full charge, as that would mean it is an ion. We also show an arrow on top of the bond that points in the direction in which the electrons are moving. Just as bond polarity deals with the distribution of electrons within a bond, molecular polarity considers the overall distribution of electrons in a molecule. Since most molecules consist of more than one bond, we must consider all of their bonds and the shape of the molecule in order to determine whether it is a polar molecule. Let's compare two examples from the Molecular Shape Lab, CCl4 and OF2. When you calculated the electronegativity difference for the bonding atoms, you saw that all bonds here are polar bonds, as illustrated below. With CCl4, although each individual bond is polar, the overall molecule is nonpolar, which means there is an even distribution of electrons throughout the entire molecule. The reason for this is as follows. Each chlorine is equally spaced in 3 dimensions around the carbon. This comes from the tetrahedral shape. Each chlorine is also pulling on the electrons within the bond with the same strength. Therefore, no side of the molecule has more of the electrons than another. Let's compare that with OF2. Once again, each individual bond is polar, with fluorine being the more electronegative. However, in this case, the fluorines are not equally distributed about the oxygen. We can see that there is a definite oxygen side and fluorine side to the molecule. Thus, since both the fluorines are pulling their bonding electrons closer, the fluorine side of the molecule ends up being partially negative.